Okay, folks, so welcome to the public oral defense of James Juno, who's going to be telling us about the project he did for his thesis. And the committee is here. I'm going to, by default, mute the people in the room. And if you wish to speak, you can unmute yourself. The easiest way to do that, if you have a laptop, is to press the space bar, and then you will be unmuted as long as you hold the space bar down. If you have trouble connecting that way, feel free to chat with the chat box or physically raise your hand. I'll be trying to look at everybody as we go forward. There are a lot of you, though, and I might not be able to see everybody at once. I can see 49 of you, but there are 61. So I might not see you physically raise your hand if you don't use the tools within Zoom. Okay. With no further ado, Jimmy, you have the floor. Oh, one other thing. Everybody in the presentation is allowed to ask questions of the speaker. No problem. Go ahead. We can't hear you. Maybe I have to unmute him.
Can you hear me now?
Yes.
Okay. That is one way to do a thesis presentation. Do you have to, is there any other formal introduction, Bill, or
Nope.
do I have the floor?
You have the floor.
Hello, everyone. Thank you all for joining me today for the culmination of my graduate studies. I've affectionately entitled my thesis research, A Deep Dive into the Distribution Function. And what I'll be talking about today is the work that I've done in developing a new tool for the numerical solution of the kinetic equation, and what new physical insights this novel means of discretizing the kinetic equation grants us, especially into the underlying dynamics of plasmas that are weakly collisional. Now, what do I mean by weakly collisional? So when it comes to the luminous universe, all of these plasmas, whether it's the heliosphere, an accretion disk, or the intracluster medium, in all of these plasmas, the mean free path, the distance particles travel before they experience and are deflected by interparticle collisions, is much, much larger than other characteristic length scales in the system. Things like the proton gyro radius or the scales of the turbulence that I've denoted by this script L. And as a practical consequence of this parameter regime, where the mean free path is so large, we know that fluid models, things like magnetohydrodynamics, that assume the mean free path is small compared to other length scales in the system, these fluid models will break down. And so we must step back to kinetic theory, or the Vlasov-Maxwell system of equations shown here. The Vlasov equation for the evolution of the particle distribution function in a 6-dimensional phase space, that's 3 spatial and 3 velocity coordinates, coupled to Maxwell's equations for the electromagnetic fields via velocity moments of the particle distribution function, like the charge density and current density. Now, this equation system shown here, the Vlasov-Maxwell system, is nonlinear. The electromagnetic fields themselves depend on the particle distribution function via these velocity moments. And as such, we expect at some point we're going to require assistance from the computer to actually model and understand these weakly collisional plasmas. But unfortunately, this equation system is notoriously difficult to numerically integrate because of its increased dimensionality. As I said before, the Vlasov equation is 6-dimensional plus time. Now, standard approaches to the numerical solution of the Vlasov equation are Monte Carlo methods, things like the particle and cell method, where this particle distribution function is discretized as a collection of macroparticles. These macroparticles are advanced along the characteristics given by the phase space flux alpha, And then these macro particles are sampled to construct the distribution function and the required coupling moments like the current density. While this approach has been historically very fruitful, there's a problem with Monte Carlo methods and the discretization of the distribution function as macro particles. And that is the pollution of your solution with counting noise. This noise is a real travesty, as the particle distribution function is such a rich tapestry of the underlying physics of a weakly collisional plasma. The wealth of data in the particle distribution function cannot be overstated. For example, just by inspection, many energization mechanisms can be identified just by looking at the particle distribution function, such as resonant processes as waves interact with the plasma, and there's a transfer of energy between the electromagnetic fields and the particles in the plasma, and vice versa. And we're further motivated to take a deep dive into the distribution function due to ever higher quality distribution function data being returned to us by modern spacecraft missions, such as the magnetospheric multiscale mission. I'm showing here data from MMS as it crosses the interface between the Earth's magnetosphere and magnetosheath, and it observes a magnetic reconnection event. What we find in these distribution functions shown here are the electrons is manifestly non-Maxwellian or kinetic structure. We have things like these crescent-shaped distribution functions indicating acceleration of particles in the plasma, as well as just generally fluctuations. And so there's a real need for new tools to help us understand this distribution function structure, to more precisely analyze the phase space dynamics of the plasma, as well as more carefully compare to observational data. I want to drive this point home with just a few images of a problem that I'm going to show in greater detail later in the talk, just to emphasize that this phase space structure tells a story. So what I'm showing here are the results of a simulation which directly discretizes this Vlasov-Maxwell system on a phase space grid. It's the evolution of the plasma in a collisionless shock.
So can I ask something here? Bill, I'm not seeing the full slides here. The bar along the bottom is blocking the bottom of the slide. I can reduce the size of the image, but then it's really quite a lot smaller. Is anybody else having this problem?
Can you hear me?
Yep.
It should be the case that if you don't touch the cursor for 3 or 4 seconds, that bar retracts. But I don't know if that's happening for you.
But I mean, I'm looking at Jimmy's screen.
Yeah.
I'm having the same problem.
So you need to have the mouse pointer away from that bottom bar for a few seconds and don't touch anything, and it should go away.
But I think
not.
it's Jimmy's computer where this has to be done, right? Because we're not.
No, it's yours.
Also, there was a message in chat. If the message in chat is unread, the bottom bar does not disappear. So if the speaking bubble is blinking, one needs to click on the bubble and then read the messages, and then it will disappear.
That might be the issue. I read that message.
That was the solution.
Okay.
That
Click
work
on
for
that
you, Jim?
orange chat thing, and it'll get rid of it, and then it'll go away.
Does that work for you, Jim?
The bar hasn't gone away yet.
There was just a new message.
Stop sending chats, people. Thank you, Darren, but no more chats for a minute, everybody. Okay, are the screens cleared?
Nope.
Have you moved your mouse away from the bottom of the screen?
I don't have my mouse down there. It's up at the top.
Another option is to come out of full screen mode and
Yeah, they've got it 50%, but then it's pretty small, which I tried. That works, but it's small.
Ian says under
Sure.
view options, you can try fit to window rather than original size.
Okay. Then it's still then it's blocked at the bottom again.
I don't know the answer. You can make it a non-full screen and then just not make it.
So Jimmy did put a link in the chat to a Google Drive that has the slides on it. This is awkward, but you could go to that, follow the slides on that while he's talking.
Well, let me ask you this. Does anybody else have this bar on it, or is it just my computer?
It goes away for me.
Yeah, mine's gone.
Wait for me.
Jim, where it says
Yeah,
chat,
I also have no problem.
Are you
Jim, where
doing
it
full
says
screen
chat,
or are you doing partial screen?
I've tried it both ways.
Jim, where it says chat, is it orange?
Yep.
Click on that.
that. That'll make it go away.
Then get rid of that window that just popped up.
Okay. Yeah,
Now
now
move
it's,
your cursor away from it.
okay, yeah.
Okay, so let's not chat unless you
Okay,
have
now
something
it's,
important to
now
say.
it's good. So I guess the problem is until everybody responds individually to the chat box, and it sits there.
No, it was yours. It was yours. People were continuing to chat.
Okay, anyhow, I can see it now.
Thanks, everybody. Crowdsourcing. All right, Jimmy, you're back.
Okay, so it's great that we've stopped on this slide because it's a huge motivation for my thesis research, that this phase-space structure tells a story. Because if you look at this collisionless shock simulation, you can clearly identify that the shock is forming structure in phase space. For example, I'm showing the protons here as a result of this collisionless shock in x Vx, and we see some evidence of a reflected proton population. If we further take cuts along these vertical lines to show the distribution function in more velocity space dimensions, in this case Vx, Vy, we identify this reflected population as a higher energy tail. And this leads to motivating questions. What is this higher energy tail? How did it get here? And how are these particles gaining energy? Now, I'm going to talk in more detail later about these questions, but what I want to emphasize from this slide is just the quality of phase space information from this direct discretization of the kinetic equation on a phase space grid. So to actually discretize the Vlasov-Maxwell system with a grid-based method, I've implemented a solver for the Vlasov-Maxwell system in the Jekyll simulation framework, which is a general purpose simulation framework being principally developed out of the Princeton Plasma Physics Lab. So with this ample motivation to directly discretize the Vlasov-Maxwell system, it's worth noting that historically, this approach is not terribly common. It's not terribly common for reasons I have previously mentioned. It's much more difficult numerically. So I'd like to spend a little bit of time on how I've overcome these numerical and algorithmic challenges. To actually discretize the Vlasov-Maxwell system of equations on a grid, I've chosen the discontinuous Galerkin finite element method for spatial discretization. Now, if you're familiar with finite volume methods, I like to think of the discontinuous Galerkin method as a natural extension of finite volume methods. Because in a finite volume method, you take your domain and you discretize it into cells, some triangulation or tessellation. And you evolve a single piece of information in the cell average. So as part of your discretization of a partial differential equation, you're only evolving one piece of information within each cell. But why restrict yourself? You could think about evolving two pieces of information, a cell average and a cell slope, and thus have a piecewise linear representation of your solution. Or you could go further, a piecewise quadratic representation, and so on and so forth. In doing so, you would gain the power of a finite element method, because you would have a higher order representation of your solution inside a cell, and thus you would have higher order accuracy. But you would preserve advantageous properties of the finite volume method. For example, the ability to retain conservation laws of the underlying partial differential equation. Just as an example, I want to show the discrete Vlasov equation. You can do this for lots of, or for every component of the Vlasov-Maxwell system, Maxwell's equations, the collision operator, etc. But I want to focus on the Vlasov equation because the Vlasov equation is going to most carefully illustrate why, how this approach works and what the algorithmic challenges are. So if we consider a phase space mesh T with some cells K sub j, and as a point of emphasis again, this would be a a phase space mesh, so up to a 6-dimensional grid with 6-dimensional cells. The problem formulation is to find this discrete representation of the distribution function, such that for every cell in my domain, this equation is satisfied, which is called the discrete weak form. Now, I've obtained this equation by multiplying the Vlasov equation by these functions w and integrating the phase space advection by parts to obtain a surface term and a volume term. Depending on your background in numerical methods, these terms may look very familiar. In a continuous finite element method, one has a very similar term to this volume term. But if you think about finite volume methods, in fact, this surface term is directly analogous. Only now, in comparison to a finite volume method, we also have these functions w that we're actually evaluating at the interface. That's what the superscript minus means. In addition to the fact that we have this capital F hat numerical flux function. And this numerical flux function is going to encode information about how the distribution function advects in phase space, or in general, how any quantity is transported. So to actually find a representation for the distribution function, we're going to expand the distribution function in these same functions w, because it's a Galerkin method. And so you have some NP number of basis functions w, and you just have to define what these functions will be. For us, we choose these functions w to be the space of piecewise polynomials of some order p. You could choose other basis sets, but we're going to find that piecewise polynomials have particularly advantageous properties for our numerical method. And so it remains to be determined what this capital F hat is, this numerical flux function. And so as an example, I want to focus on the streaming term, v.grad f. For the streaming term, because the advection is given by velocity, and because we have a velocity grid, we could do something called upwind fluxes, where we're explicitly encoding the direction the distribution function is going to propagate in our domain. If the velocity is greater than 0, then the distribution function should move from left to right. So we're going to use the distribution function on the left half of the surface interface. And if the velocity is less than 0, the distribution function should move from right to left. And so we'll encode that with the distribution function on the right side of the interface. So as I said before in the motivation for the discontinuous Galerkin method, one of the things that we retain from finite volume methods is the ability to preserve conservation relations. And so what I want to examine is, as a result of our spatial discretization, what do we retain that the continuous system also preserves? So we know that the continuous Vlasov-Maxwell system has a number of conserved quantities, formally an infinite, but let's focus on just a few, especially the density and the energy. So how do we determine what our spatial discretization respects? Let's return to the discrete weak form. In the discrete weak form, these functions w, because the discontinuous Galerkin method is a Galerkin method, we can plug in for w anything I can represent with my solution space. And now it's perhaps a bit more obvious why we'd like to do piecewise polynomials. For example, if we take w equal to 1, a constant function, so long as we can represent a constant function, this is a completely fair thing to do. The volume term is going to vanish because the gradient of a constant function is 0. And if I sum over all cells, in fact, this surface term will also vanish. And the reason the surface term vanishes is because the flux into one cell is equal and opposite in sign to the flux out of its neighbor cell. I don't want to create or destroy flux, so flux across a surface interface had better be preserved. And so when you sum over cells, these surface contributions should pairwise cancel. The result, as you can see, is the sum over the number of cells of the integral of the time derivative of the distribution function. This is density conservation, or if we multiply by mass, mass conservation. We can do a similar thing with substituting other functions for w. For example, if we use quadratic basis functions, we can represent 1/2 mv squared. And when we plug in 1/2 mv squared, again sum over all cells, and now sum over the number of species in the plasma, the surface term will vanish, and we're left with a discrete analog for the time evolution of the 1/2 mv squared moment of the distribution function. This is the energy. And in fact, the time evolution of the energy is exactly what we expect. It's the discrete analog of the exchange of energy between the particles and the fields, J dot E. So using polynomials for our basis set, our spatial discretization can retain properties of the continuous Vlasov-Maxwell system. With that in mind, we can ask what actually are these polynomials and what form should these polynomials take? As an example basis, we can consider a nodal basis, where the polynomials are defined to take the value of 1 at each of these C sub k nodes and 0 at all other nodes. Example nodal bases are something like this, where the top row is a one-dimensional basis, the middle row is a two-dimensional basis, and the third row is a three-dimensional basis. And then the first column is piecewise linear, the second column is piecewise quadratic, the third column is piecewise cubic, and the fourth column is piecewise quartic functions. Now, this is just an example of a nodal basis. Other examples of nodal bases are things like hat functions, if you're familiar with the finite element literature. This particular basis set is called the nodal serendipity basis set. It's in fact related to other basis sets, like a pure tensor product basis set, just by elimination of some degrees of freedom. For example, the piecewise quadratic in 2 dimensions basis set would add a node to the middle of the domain here. I've made all these points about this specific form of basis functions because it leads naturally into what is one of the first challenges of actually discretizing the Vlasov-Maxwell system. Now, for the actual DG discretization, we're going to have to evaluate integrals. For example, in this discrete weak form, we've got these integrals over cells and these integrals over surfaces. So how should we evaluate these integrals? Well, one thing we could do with the nodal basis, which would be an exceptionally cost-efficient scheme, would be to directly plug in the value of our expansions at the nodes, because we know the value of the functions at the nodes just by definition of the nodal basis. However, this would incur what are called aliasing errors, because the product of the 2 expansions is not contained in our basis set. So this quantity alpha times f is not in our basis, and multiplying alpha at the node times f at the node is going to incur an integration error. Well, this may not be that big of a deal, because in fact, there are many applications of DG where one can incur these aliasing errors and do some sort of mitigation or overall tolerate these errors just because the scheme is so much more cost efficient. However, for the kinetic equation, it's important to recall that these conservation relations, things like conservation of energy, are implicit to the Vlasov-Maxwell system. And that means that aliasing errors could be catastrophic. If you consider the time evolution of the 1/2 mv squared moment of the Vlasov equation, the evolution of the energy, remember that it's J dot E. It's a quadratic term. And so by incurring these aliasing errors, we would then be incurring errors in the actual energy exchange between particles and fields. Not only is this physically inaccurate, it's potentially completely catastrophic for the stability of the scheme. So this naturally leads into challenge number 2. We could use a sufficiently high order quadrature, some NQ number of quadrature points, to eliminate these aliasing errors. And that would naturally make the computational complexity of the scheme the number of quadrature points times the number of basis functions n sub p. In doing so, we would obtain a very expensive numerical method, because n sub q can be quite large for actually exactly integrating the nonlinear term. So let's take a little bit more careful look at exactly what the fundamental operation of our numerical method is. If we expand the phase space flux and the distribution function in our basis set and look at the volume term, this gradient of a basis function dotted into the phase space flux times the distribution function. This is actually a tensor convolution. It's a rank 3 tensor of 3 basis functions dotted into our coefficients for the phase space flux and the distribution function. Naively, this tensor is dense, and this is no better than direct quadrature. If you're trying to evaluate a function that requires the number of basis function cubed components, you're going to run into the same issues in terms of a very expensive numerical method for integrating the kinetic equation. But if we consider a different basis set, in this case, a modal orthonormal basis set, then by virtue of the basis being orthonormal, some of these integrals of triple products of basis functions would vanish. And then this tensor would be sparse, and the resulting update could have a dramatic reduction in the number of operations required. So I show now a computational complexity experiment in the amount of time it takes to update a single cell for a variety of dimensional combinations of the kinetic equation and a variety of basis sets. For example, the previously mentioned tensor basis and serendipity basis. I'm showing here in the top plot just the computational costs of v.grad, the streaming term, and in the bottom, the full phase space update, alpha dotted into the z gradient. Importantly, this computational complexity is much more favorable than direct quadrature. At worst, for the full phase space update, we find that the cost of the scheme scales like the number of basis functions np squared, k equal to 2. And if we compare this to actually direct quadrature, for a 6D simulation, this is a factor of 40 reduction in the number of operations. So using an orthonormal modal basis, we can both reduce the cost of a direct discretization of the kinetic equation to acceptable levels while respecting the requirement that our scheme eliminate aliasing errors so that we can accurately treat things like the exchange of energy between the particles and the fields. This naturally leads into the physics that we'd like to do with this new scheme. So all of this effort, all of this sweat and tears, and if we're honest, a bit of blood that goes into code development, now leads us into what can we actually do with a direct discretization of the kinetic equation. So I call this section fully leveraging phase space. And I'm going to focus again on the collisionless shock simulations that I showed as part of the motivation, especially with novel diagnostics applied to the results of these simulations. I've mentioned collisionless shocks a couple of times, and it's worth being more precise about what I mean by a collisionless shock. So a shock wave in general is any disturbance propagating faster than the local speed of sound. And these sorts of nonlinear waves are ubiquitous in astrophysics. But remember, we're considering weakly collisional plasmas here. And so the mean free path of interparticle collisions is very large. Thus, many of these shock waves will actually convert their large kinetic energy from their supersonic flows to other forms of energy via collisionless processes, because the shocks will steepen to scales smaller than the mean free path. Just as an example of a system where collisionless shock is present, consider the Earth's bow shock. It's a bow shock in the most traditional sense. The solar wind is coming in from the left here at supersonic speeds, and it's encountering the Earth's magnetic field as an obstacle. So just like a bow shock that forms with a supersonic flow around a cylinder, we have a bow shock as a result of the supersonic solar wind interacting with the Earth's magnetic field. But remember that the mean free path in this system is very large. I showed, for example, the heliosphere mean free path at the beginning of the talk. It's order 1 AU, or 10 to the 8 kilometers. And this bow shock actually is observed to be on the order of 10 to 100 kilometers. So much smaller gradient length scale than the mean free path. So this naturally leads into questions about how this energy conversion is actually happening. How is this incoming supersonic solar wind converting its kinetic energy to other forms of energy as the flow stagnates and shocks across the Earth's magnetosphere? Just as an example of ongoing observations that further motivate this discussion, I'm showing again data from the magnetospheric multiscale mission. This figure is adapted from a recent physical review letters by Chen et al. And a bow shock crossing of MMS observed quite dramatic increase in the electron temperature, as well as the corresponding distribution function structure associated with this increase in the second moment of the distribution function. And so again, we're begging the question of in means of interpreting this distribution function structure. So we've motivated a continuum discretization of the Vlasov-Maxwell system because we want to actually dive into this phase space structure. But it would be helpful to have other means of actually interpreting the phase space structure as opposed to just creating Rorschach plots of phase space. And the way we're going to assist ourselves in interpreting this phase space structure is a novel mechanism or a novel diagnostic for understanding plasma energization. So to actually motivate this new diagnostic, I want to return here to the Vlasov equation and again consider the 1/2 mv squared moment of the distribution function, the energy of species S. The evolution of the energy in time has a number of terms in it. Just by taking the 1/2 mv squared velocity moment of the Vlasov equation. You have a number of terms for the flux of the energy, how the energy is moved around, for example, energy flux or heat flux. But importantly, the exchange of energy between the plasma and the electromagnetic fields is governed by the electric field, this US.E term. This is important because it suggests that the electric field is a extremely important component of the actual energization in phase space as well. So if we step back from integrating over velocity space, and instead consider E dotted into the velocity gradient of the distribution function, a quantity I'm going to call C sub E, we can gain new insights into the actual phase space evolution of the energy and how energy is exchanged. We don't have to consider it just in this form. We could also consider time averages of this quantity. And this diagnostic is called the field particle correlation and was pioneered by Klein and Hauss in 2016 and expanded by Klein and Hauss and their collaborators in subsequent papers. If you're not familiar with this diagnostic, it may seem a bit strange. What use is actually directly looking at E dotted into the velocity gradient of the distribution function? So I want to consider a simple example before I try to apply this to a collisionless shock. And that is Landau damping of a Langmuir wave. So what I'm showing here is an electric field perturbation that is damping in a collisionless plasma. Now, our canonical picture of Landau damping, at least of a traveling wave, is particles moving slower than the phase velocity of the wave can gain energy by essentially surfing the wave. And we can ask, what does the field particle correlation give us as far as a signature of this Landau damping process? So what we observe is that around the phase velocity of the wave that we're simulating, we have this blue-red signature. And what this blue-red signature corresponds to is a loss of phase space energy density on the slower side of the phase velocity and a gain in phase space energy density on the faster side of the phase velocity. This signature corresponds to the actual energization of particles. Particles are moving from the blue, phase space energy density is moving from the blue region to the red region. And because in our picture, as we can see, there are more slower particles than faster particles, more particles gain energy from surfing the wave as opposed to lose energy by being slowed down by the wave. And I'll note that this particular correlation is done with some amount of time averaging over more than a wave period of the wave. So having defined this diagnostic, now let's move to a collisionless shock simulation. And so what I want to focus on is a one-dimensional perpendicular collisionless shock. By perpendicular, I mean that I'm going to initialize a magnetic field that is perpendicular to the shock normal, the direction the shock is propagating. And so the particular geometry I'm going to use today is a magnetic field in the z direction, an electric field in the y direction that will set up an E cross B velocity, in this case that is super alphenic and also supersonic. And I'm going to show in this movie the actual evolution of a shock wave, a steepening of the magnetic field and an energization of the electrons and the protons.
So Jimmy, can I, oh, go ahead.
No, I was trying to pause the movie. Yeah, go ahead.
So can you describe how you're doing this? Are you pushing somewhere, or are you setting up an initial condition, or
Yes. So on this right wall here, I'm going to inject plasma. And on this left wall here will be a reflecting wall. So I have some incoming supersonic and superalfanic flow. It's going to reflect off the wall. And as a result, the colliding of these two supersonic flows will produce a shock wave that then propagates from left to right. The simulation domain, by virtue of this setup, is done in the rest frame of the downstream plasma, which is why you'll see the shock propagate from left to right.
Okay, so but you start off on the right side with a push or a continuous oscillation, or
it's a continuous injection of plasma.
so isn't that build up mass then if you have a wall on the other end?
So the number density of this simulation does increase linearly with time, because I'm constantly injecting mass.
All right.
And so we see
Jimmy, what's the mass ratio? Is it real or not?
Oh, mass ratio 100.
Okay.
So the protons are supersonic, but the electrons are subsonic. And the result, as we can see, is a movie of the the snapshot I was showing before, with the reflected proton population and a steepening of the magnetic field that then propagates from left to right. So we observe a compression of the electrons and a reflected population of the protons. And we can then ask, how is this shock actually energizing the particles? How is this incoming supersonic flow being converted to other forms of energy, like electromagnetic and internal energy? So I want to focus on the protons at first, exactly the same plots that I was showing before, but now really getting into the details. So what I'm showing in this top plot here is, again, the shock in X, Vx, along with the electromagnetic fields in X, where you see the steepening of the magnetic field and the reflected proton population. And if we consider cuts of the proton distribution function in Vx, Vy, and then apply this field particle correlation, we start to get some signature associated with this higher energy tail. So I'm going to focus on this particular case here and try to understand what exactly this signature is here that seems to correspond to at least some energy exchange. If I zoom in on this tail and just focus on the energy exchange due to the Y electric field, and note that I'm transforming the Y electric field to the shock frame. I'm doing a Lorentz transformation. We observe a similar signature to what we were seeing in the Landau damping example, where you have some loss of phase space energy density and some gain of phase space energy density. And it coincides with this signature of the reflected population and higher energy tail. So what's going on here? Well, for starters, we want to note that this is actually an energy gain. If I integrate this quantity, C, E, Y, over the entire velocity space to actually determine what the overall exchange of energy is, it's positive. At this point in time, these particles are gaining energy. And so we can ask, why are these particles gaining energy? And to do that, I'm going to turn to intuition from single particle motion. So if I have protons E cross B drifting into a magnetic field gradient, they can actually sample both the upstream and the downstream. And historically, this has been called shock drift acceleration, where if you have protons that move into a magnetic field gradient and then are turned around by the stronger magnetic field, when they return upstream, they gain energy along the electric field associated with the E cross B motion and are thus energized. To focus on a single particle, if I have some incoming proton in some smaller magnetic field and it crosses into a region of a larger magnetic field such that it can be turned around, such that its gyro motion then moves it back into the region of smaller magnetic field, well, now it has an extended region by which it can be accelerated by the Y electric field, the motional electric field, before it moves downstream. We can see this picture in phase space directly. If I have some particle that's moving at the velocity denoted by the star, and it has some gyro motion, when it crosses into the region of increased magnetic field, the magnetic field is larger, so it has to gyrate faster, and its overall velocity has been reduced to this green star. But because of its gyro phase, when it crossed into the region of large magnetic field, it returned upstream and then assumes this red trajectory where it is now gaining energy. And it is no coincidence that this red trajectory of just this single particle coincides with the region that's being energized in phase space. So what we're identifying here for the first time by virtue of having a continuum representation of the Vlasov-Maxwell system is a phase space energization signature of shock drift acceleration. So while this energization mechanism has been studied in the past using a Lagrangian perspective, for example, tracking single particles, we now have a complementary way to understand this energization mechanism by looking directly in phase space and also being able to compare more directly with observational data of the distribution function. I haven't forgotten about the electrons, so let's turn now to what's going on with the electrons in this system. So we noted that the electrons are being compressed as a result of this shock. And I want to focus this time on this region of compression at 20.5 dP, the 20.5 proton inertial lengths, and try to understand what this sort of splotchy field particle correlation is. Again, focusing on just the Y electric field, I'll note that now what we observe is a slight asymmetry in the magnitude of the correlation. So this actual region in physical space corresponds to this star, a net positive change in the energy. And what we're observing is actually the electrons gaining energy due to an alignment in grad B drift and the motional electric field, EY. So because the electron gyro radius is much smaller than the gradient length scale of the shock, the electrons stay well magnetized through the shock. Because they stay well magnetized through the shock, they drift as a result of the grad B drift. And because the grad B drift is aligned with the motional electric field, the Y electric field, we observe net energization. And this process is called adiabatic heating. So now, in addition to the phase space energization signature of shock drift acceleration, we now also have a phase space energization signature of what's called adiabatic heating. So that concludes just one application of the Vlasov-Maxwell solver to kinetic systems of interest in astrophysical plasmas. I kind of want to just leave it as at a summary for right now, that direct discretization of the Vlasov-Maxwell system is challenging but worth it. So we've done a number of algorithmic innovations which have allowed us to develop a robust, cost-efficient, importantly grid-based Vlasov-Maxwell solver, which gives us access to a noise-free distribution function and allows us to probe the details of phase space dynamics. For example, we've directly diagnosed the energy transfer in phase space as a result of shock drift acceleration and adiabatic heating. As another point of emphasis, this Vlasov-Maxwell solver that I've implemented in the Jekyll simulation framework is open source, and I do feel like this is a very powerful tool for the solution to the kinetic equation. The collisionless shock simulation that I touched on today is only one of many applications that we're pursuing with the Vlasov-Maxwell solver. I'm showing, for example, in this movie, the evolution of instabilities driven by counterstreaming beams of plasma and the overall competition of these instabilities. I can talk in more detail about this particular application, but for now I do want to turn it over to the committee and the audience for any questions about what I've shown up to this point.
Yeah, Jimmy, can I ask one more question?
Absolutely.
In the shock simulation you just showed, the mean free path, meaning the dynamics in the z direction, is not playing much of a role, right? This is mostly perpendicular.
It is an entirely perpendicular collisionless shock. You would still have if you're referring to like parallel streaming versus perpendicular, I'm in
And
general.
And Landau effects, if I'm referring to Landau effects also, they're not there, right?
Yeah, so there is no there's no parallel electric field in this particular simplified setup.
Okay. Just wanted to check.
Yeah.
This is a good time for anybody from the audience of 63 who wants to throw in a question. Just unmute yourself and speak up.
Okay, hello, Jimmy.
Hello.
Hi. Very nice presentation.
Thank you.
There were a couple times where you seemed to imply that PIC and other Monte Carlo methods are not appropriate or less appropriate to study phase space dynamics. Perhaps you didn't mean it in as blanket of a way, but could you elaborate more and perhaps quantitatively? Do you have any quantitative comparisons about the limitations of those kind of methods versus what you've developed?
Sure. I want to make the point that, you know, regardless of whether or not you're doing the particle and cell method or this approach with a grid-based Vlasov-Maxwell solver, you're still solving the same equation system. And so you're still modeling a kinetic plasma. The question becomes, what can you gain from one approach versus the other? And I do think it is the case that when you directly discretize in phase space, you have access to a much higher quality of phase space dynamics. If I can show just a supplement slide, not a lot of context, but related to this other application that I was showing, we've done some comparisons of the phase space dynamics of these types of instabilities driven unstable by counterstreaming beams of plasma, comparing the Jekyll results to different different numbers of particles in cell. And so this middle plot here is a low number of particles per cell in both cases, 12 particles per cell, whereas the far right is 12,000 particles per cell. And the one of the points that we've tried to make as far as the utility of our continuum Vlasov-Maxwell solver is that you do gain tremendous accuracy in phase space by virtue of this grid-based approach. For example, this low particle per cell count is motivated by the number of particles per cell that are used in. Go ahead.
Quick question. Sorry, the each row is a different time step during.
Yeah, each row is a different point in time, and these are
all right. Thank you.
Yeah, and what this middle row is motivated by a particle per cell count of typical simulations, for example, of shocks that they observe these instabilities. What we actually find is that the phase space resolution in some of these low particle per cell counts is poor enough that it actually can pollute the macroscopic dynamics. In general, though, it's interesting to note that there's a lot to be gained just by having access to a higher fidelity representation of the distribution function. When I made this point about the utility of the field-particle correlation.
Sorry, Jimmy, before you move, okay.
Wait, I can move back. I was just going to make one more.
Oh, please, yeah.
I feel that this diagnostic is potentially very valuable, but one of its forms requires gradients of the distribution function. And so it can be difficult to get enough phase space resolution with a particle and cell code to properly leverage diagnostics like this. There are plenty of examples of the particle and cell method, usually run with quite a large number of particles per cell that then allow you to diagnose phase space dynamics. For example, there have been particle and cell simulations of the magnetic reconnection event I showed at the beginning of the talk, where they do find the crescent-shaped distribution functions. But again, this complementary approach, this direct discretization, does allow for quite detailed probing of phase-space dynamics.
Great, thank you. As a follow-up, when you had the low resolution, high resolution PIC simulations, how does the performance of the discrete, sorry, the
How do the cost of the two methods compare?
yeah to your scheme?
So the continuum Vlasov-Maxwell method for that particular problem was about the same cost as an 1,000 particle per cell run.
Okay.
So I was showing 10 particles and 10,000 particles per cell. So we were in between these two limits. Yeah. In general, it is worth noting that this approach is on average more expensive, but it's not more expensive in a accuracy to cost sense. If you require high phase space resolution, I believe that the Vlasov-Maxwell solver on a grid is a very much the tool to use, especially when you're probing very, very precise dynamics, things that may require extremely high signal to noise ratio. So we're all kind of working towards the same goal of scientific enlightenment.
So Jimmy, this is Jim Drake. Can I ask a question also?
Yeah, absolutely.
So you showed data from a completely perpendicular shock.
Yeah.
And of course, one of the things that everybody's interested in, or many people are interested in, is the production of energetic particles at shocks. And typically that process is much more efficient if you have an oblique shock.
Yes.
And especially then the question is, if you are trying to look for particles that gain a lot more energy than in the initial state, in other words, very energetic particles compared to their initial average energy. Have you tried looking at how this continuum approach works? And can you really span an enormous range of energies that's required to do this kind of calculation?
Right. I think it's worth emphasizing with a grid-based approach. You know, you are limiting yourself to a velocity grid, and so depending on exactly how energetic you expect the particles to become, this does set kind of a limit on what your phase space should look like. We've done simulations with very large phase space extents. For example, just in this movie here, the simulation is starting with plus minus 32 of the initial thermal velocity. So it's very much within the realm of possibility to do Vlasov-Maxwell simulations with very large phase space extents. However, it is worth emphasizing that when you're talking about looking at energetic particles that maybe have gained orders and orders of magnitude of energy, it could be challenging to actually span enough velocity space to accurately resolve that. Though when you have a grid-based method, you can also use different velocity space grids to potentially span this space. So, for example, Jekyll supports general non-uniform grids, and you could think about doing a logarithmic grid in velocity space so that you could go to essentially extremely high velocities and potentially model power laws or higher energy tails.
Thank you.
On following on Jim's question, so in a PIC simulation kind of thing, you're following macro particles, or in test particle simulations, you follow individual particles, so you can make them relativistically consistent, and it's fine. A number of years ago, I bugged Rudolf Treumann and then later George Levitt-Iotis about what does F look like if you do this fully relativistically, and they wrote a couple of papers on this, because it turns out that it's not easy to define F anisotropically or generally for relativistic stuff. I mean, there's the Maxwell-Juttner distribution, but that's an isotropic Maxwellian in the relativistic limit, right? So but what happens if I don't see any reason why you'd ever expect it to be isotropic in say like a supernova remnant shock or something. So the question is you sure you can ramp up your range of velocities for phase space, but how do you get over the issues of relativistic effects? Is that a trivial thing to implement, or is it a nightmare?
So the current Vlasov-Maxwell solver is non-relativistic. However, we've done some thinking about how to generalize this grid-based method for the relativistic system, and it does have its challenges. For example, I motivated the discontinuous Galerkin method for this particular system because we could conserve the energy. It's more challenging to construct a conservative method for the relativistic system because of the gamma factors. But it's not impossible, and it's something we've thought about. And in fact, if we were going to consider systems that produce energetic particles with a grid-based method, it is my opinion that it would be more natural to make sure that the Vlasov-Maxwell solver you're using is relativistic, and you solve things on a momentum grid so that you can more naturally go to very, very high energies.
Plenty of time for more questions. Anybody else? While you think about your questions, let me just comment how exciting it is to be able to do a defense of a thesis with so many people from off-site. I appreciate everybody joining in, and I hope that in the post-COVID world, we basically do all defenses this way, because it looks like a much better way to get the word out.
I'll ask a quick question. Jimmy, very, very interesting work. We haven't talked much about the physics. So in the perpendicular shock problem you showed, it looks like maybe the electrons are conserving mu and the ions are not. Have you ever tried to measure, I don't know, some change in entropy? How much of it is just adiabatic heating for electrons and how much is not adiabatic for the ions?
So for the actual heating in this particular shock, a significant percentage of the electron heating is adiabatic. In fact, what we find is if we consider the essentially requirement for the particular electron energization mechanism that we found, where the grad B drift of the electrons is aligned with this motional electric field, it turns out that the actual requirement for this to be true is that mu is conserved through the shock width, so that the electrons stay well magnetized through the entire shock. So you can go through the argument of what is the rate of change of the energy of the electrons if it's due to the grad B drift dotted into the Y electric field, and you find that this naturally leads to the spatial gradient of the magnetic moment is 0. In fact, this is principally why it's called adiabatic heating. The proton energization is basically all not adiabatic because the result of the proton energization is that when the protons cross the gradient of the magnetic field, they're able to move back upstream. Essentially, when they get turned around, they're not technically well magnetized through this process. It's not like mu is conserved. So they're crossing into a magnetic gradient. Depending on their gyro phase, they are deflected back upstream, and then they gain energy in this way. As far as entropy change, one thing I didn't focus on in the talk because it's something we're still actively working on. If I zoom to the end of this movie, essentially what the downstream region of the plasma looks like as a result of the shock, especially for the protons, we observe actual fluctuations in phase space and also fluctuations in the electromagnetic fields. So there's this real question about how do collisionless shocks actually dissipate their energy? The mean free path is so long or so large for these systems. What mechanisms are actually leading to entropy production? And it would be interesting to actually diagnose what's going on in the downstream region of these shocks, where there seems to be so much fluctuations in the electromagnetic fields and phase space. There's no secular energy change. The shock is done energizing the plasma, but there's lots of oscillating energy and a continual creation of ever smaller scale gradients in velocity space. So I think there is a really exciting avenue of research in collisionless shocks to take some of the phenomenology that people have worked on in the turbulence context of information going to arbitrarily small scales in velocity space and being dissipated by collisions, applied to the downstream region of a collisionless shock.
Can I then ask another question? This is Jim again.
Yeah.
Back to that slide you just had. You have reflected ions, and that I think implies that this shock is a real shock in the sense that there's some dissipation process going on. If you reduce the velocity of the inflow, do you ever reach a point where you don't have any more reflected ions and therefore you don't really have a shock? And have you explored that territory?
I haven't explored the physics of that territory, but as part of the picking of the parameters for this particular shock, it was the case that we were looking for kind of the lowest velocity shock that still produced a reflected population. This is in the literature I've read, these shocks that have reflected proton populations are called supercritical shocks, because you require the some sort of reflected population to actually convert the upstream kinetic energy into other forms of energy. There's no smooth transition from upstream to downstream. And we have done simulations of lower velocity, quote unquote, shocks, but not analyzed them. We were, in this case, probing parameter space to find a relatively low velocity shock that produced some amount of reflected protons.
Okay, so that was really my question,
like
is whether you had looked at a subcritical shock, and so you've done that, but you haven't really diagnosed it.
Correct.
Very good.
I was just going to say, Jim, that I would argue that just because it doesn't reflect ions doesn't make it a non-shock, right? I mean, there's certainly lots of shocks that don't show any evidence of reflecting ions.
Right. So really the question is it a real shock? And then how do you define what it is? And how does dissipation actually take place if you don't have ion reflection?
There's definitely especially interesting physics to be done, potentially with a continuum Vlasov solver, because you can diagnose these sorts of wave interactions for subcritical shocks where you might have dispersive processes through the shock, essentially waves mediating the actual energy conversion. I feel like this is a potentially very exciting application of the continuum Vlasov solver, where you can really diagnose wave particle energy transfer very carefully.
I have a quick question, Jimmy. The simulation that's shown, the evolution of the perpendicular collisionless shock, can you describe how much computational resource we're looking at in the making of this?
The particular simulation shown cost about 1,000 node hours on Stampede 2, so order 50,000 core hours. And the actual grid resolution was 1,536 grid points in X and 64 grid cells in the velocity dimensions.
64 cubed or 64 squared?
64 squared. Since the magnetic field is out of the plane, we only require the Vx, Vy components of velocity space.
Okay. And what order of polynomials were you using here?
Quadratic.
Okay, I'm going to pause for 5-10 seconds to let the folks in the audience find the unmute button and ask their question if they have one. Good. So here's how this goes now. Those of you who are not on the committee and who are not Jimmy are free to stay on this Zoom link or to check back from time to time. We're going to step away for a private part of the examination. I don't know how long that takes. We're going to start with a quick bathroom break because I'm getting to be an old man, and then we'll get started with the questions. And when we're done, Jimmy will return to this space. So if you're wondering at what phase we're in, if you come back and you're looking around, if you see Jimmy, we're close to the end, and if not, there's no white smoke coming out of the cathedral yet, out of the chimney. After that, then I don't know how those, you could all be thinking about virtual champagne toasts in case, you know, not to get ahead of myself, but you can't go out shopping, but you could look around, you know, in case you want to do that in an hour or two. So this will remain live, and some of us are going to vanish here in a second. If anybody has a question, go ahead. And I added a bow shock since you brought the bow shock back. Here we go. You had a question, Jimmy?
I was just going to stop recording if there were no further public questions.